Hello everyone. I hope everybody is fine and healthy and ready for just another lecture in continuation of lectures for curve sketching. Today I want to talk about concavity. What is concavity? Let's consider part of a graph of a function. It could be a polynomial, a parabola, whatever. And if you look at this graph, if I draw tangent lines at different points, you will notice something. See the tangent line here, tangent line there, tangent line here, tangent line there. If I draw a tangent line at different points on the graph, you may notice that the whole part of the graph is above, I repeat, above those tangent lines. If something like this happening, we say that the graph is concave up, okay? So it has a cup shape. The graph has a cup shape. So if you draw the tangent lines, as I said, the whole part of the graph is above these tangent lines. So in these cases, we say that the graph is concave up. So I'm going to write down here concave up, okay? And then on the other hand, if you have another type of graph, like the one on the right-hand side, where when you draw the tangent lines, all these tangent lines are actually above this graph, or you say the graph is completely below all of these tangent lines. If something like that happening, we say that the graph is concave down. So this one is concave down, the other one is concave up. This one has a cap shape. So cup and cap, basically, all right? You may think of this first graph. If you think of this as a container, actually here the graph holds water, all right? But here it doesn't hold water. If you just pour water, because of the concavity of the graph, the water is not going to stay inside the container as it did in the previous case. The water is going to be pouring out. So we have two situations. Either the graph is concave up or the graph is concave down. Now, sometimes, of course, the graph changes its concavity. For example, you have a part of a graph right here, which is concave up. And then at this point in the middle somewhere, it changes its concavity from concave up to concave down. Such points have special names. We call them inflection points. So if somebody asks you what is an inflection point, you're going to say an inflection point is a point where the graph changes its concavity. Now, in this graph right now, in this image, the graph is changing its concavity from concave up to concave down, but it could be like it's changing from concave down to concave up. For example, it could be something like this. Here, this part of the graph is concave down clearly, and then it changes concavity. It becomes concave up after this so-called inflection point. So this is an inflection point, that's an inflection point, or wherever you see that the graph changes concavity, that's an inflection point. Now, another thing, if you look at these tangent lines from left to right, you see that the slope of these tangents are increasing. Like the slope of tangent here at point A is greater than the slope of tangent here at point B. So we see that the rate of change of slope is actually positive. And the slope is related to the first derivative. And when we talk about rate of change of slope, it means we're talking about the derivative of the derivative in other words. In other words, we're talking about the second derivative. So we can say that in graphs that are concave up, we can say that the second derivative is positive. So a function f of x is said to be concave up on an interval if I can write here the second derivative is greater than 0. And a function is said to be concave down on an interval again if the second derivative is less than 0, which means it's negative, okay? So what you just need to remember is that if the second derivative is positive, the graph is concave up. If the second derivative is negative, the graph is concave down, period. That's all you need to remember. So there's something called the test for concavity. The same thing, if f double prime of x is positive for all x in a given interval, then the graph of f of x is, of course, it's concave up. And if f double prime of x is negative for all x in that interval, the graph of f of x is concave down. Okay, so we have a function here. It's a rational function. I'm going to do an example. It says determine the intervals of concave up, concave down for this function, and find any inflection points if it has. Mind you that not all graphs have inflection point. Imagine the famous parabola y equals x squared, for example. It is a function that is always concave up, and it never has an inflection point. So we are not saying that every function in the world would have an inflection point. If it has inflection points, we need to find it. Okay, for this purpose, our criteria of judgment is the second derivative, as I said earlier. So I have no choice rather than finding the first and second derivative of this function. So I'm going to find the derivative by using the quotient rule, which you know very well. So derivative of top times bottom minus derivative of bottom times top over the denominator squared. So if I simplify, I'm going to get negative x squared plus 1 over x squared plus 1 all squared. I suggest you do these questions by yourselves one more time, and you watch these lectures multiple times. Every time you watch the video, you learn just a little bit part of it that you probably missed in the first time of watching. Now, the second derivative would be the derivative of the derivative. So derivative of the top is negative 2x times the bottom. I'm applying the quotient rule, minus the derivative of the bottom, which is 2 times x squared plus 1 times 2x. That's the derivative of the denominator. I use the chain rule. Times the numerator, which is 1 minus x squared. 1 minus x squared over the whole denominator squared, which is x squared plus 1 raised to x power of 4. Now, in the numerator, I see that x squared plus 1 is a common factor. If you don't mind, I'm going to factor it out in the numerator because I want to simplify as much as I can. So x squared plus 1 exponent of 4 in the bottom. But in the numerator, I'm going to factor it out. So I end up with negative 2x times x squared. That's negative 2x cubed. And then minus 2x. And then I have negative 4x times 1 minus x squared. So negative 4x times 1 is just negative 4x. And negative 4x times negative x squared would be positive 4x cubed. All right. So I simplify one factor from the top and the bottom. So in the denominator, I end up with x squared plus 1 to the exponent of 3. In the numerator, I just have to collect like terms if there are any. 4x cubed minus 2x cubed, that will be 2x cubed actually. So let me collect like terms. And in the bottom, we have minus 6x. I can even factor the numerator. 2x is the common factor. Factor it out, you get x squared minus 3 over x squared plus 1 all cubed. So that's what we end up with. Okay, so I found the second derivative, finally. And now, in order to determine the sign of this second derivative, I have to set it equal to 0 because I want to find out over what interval this giant rational expression is positive and over what interval it's negative. So for this purpose, we always set the second derivative equal to 0. I put in a bubble because of its importance. And then I'm going to set the second derivative I got earlier equal to 0. We know that a fraction equals 0 whose numerator is equal to 0. So either 2x is 0 or x squared minus 3 equals 0, which means that either x is 0 or x is plus minus square root of 3. So I found 3 x values, to tell you the truth, where the second derivative is 0. Now, these are called potential inflection points. So these could be where the graph has its inflection points, and I'm being suspicious right now. There may be like 3 inflection points at x equals 0, x equals negative root 3, and x equals positive square root of 3. I have this suspicious, but we can't say for sure that these are inflection points yet, unless we make sure that the second derivative does change its sign. Because if it doesn't change its sign, then it will not be considered as an inflection point. So it's extremely important. These, at this point, I can say these are potential inflection points, not 100% inflection points yet. If I construct my chart later on, if I figure out that the second derivative did change its sign, then I'm going to say, okay, so they are actually inflection points. But for now, they're just good candidates to be an inflection point. So for this purpose, I'm going to write 2x, that's one factor in the numerator in my chart. X squared minus 3 is the second row in my chart. Then I have the denominator, which I should not ignore, because its plus minus sign might influence the whole sign of the second derivative. So I have to take that into account. The sign of the denominator also counts. And 2x is 0 at 0. The roots we had were negative root 3, 0, positive root 3, and 2x is 0 at 0. So to the right would be positive, to the left would be negative. X squared minus 3 is 0 at 2 points. Once it's 0 at root 3, and once it's 0 at negative root 3. So if you pick any number in between these two roots, such as, let's say, 1, and you plug in, you will end up with a negative answer. So x squared minus 3 has a positive sign if x is greater than square root of 3. It also has a positive sign if x is less than negative square root of 3. But it has a negative sign when x is in between positive and negative square root of 3. X squared plus 1 is an always positive expression. If you cube it, it's going to be always positive. So I'm not going to put any 0 in this third row of the chart. And I'm going to claim that this whole expression is always positive. When you cube an always positive expression, what do you expect to get? You end up with a positive answer anyway. Now, the product and the quotient of all these 3 factors will determine the sign of the y double prime. So this first interval would have a negative sign. Negative times negative is positive, then negative and positive signs. These are the signs of this second derivative of the function. Where y double prime is 0, well, wherever the numerator is 0, y double prime is also 0. And we knew that is happening at 3 points. Now, I see in the first interval, the second derivative is negative. And we said earlier that if the second derivative is negative, the graph is concave down. So I'm going to write CD, which stands for concave down. So the graph should look like something like this. And then we have concave up for the next interval from negative square root of 3 up to 0. So the graph is concave up. And then back again, it's concave down. And then again, concave up. So we see that over different intervals, the graph is concave down. Over different intervals, it's concave up. So look at the first x value, negative square root of 3. See what happened. The second derivative was equal to 0. We said that it's a good candidate to be an inflection point. But we waited to see if the second derivative does change its sign or not. And now here you see that it exactly changes its sign from negative to positive. So that means that negative root 3, that point whose x-coordinate is negative root 3, is indeed an inflection point because the second derivative did change its sign, which means that the graph changed its concavity at that point. And that was the definition of inflection point, if you recall. We said that inflection point is a point where the graph changes its concavity. So here, at this point, I'm going to have my first inflection point. This is an inflection point. And then I see at 0, again, it changes its concavity this time from plus to minus, rather than from minus to plus. So still that counts as an inflection point. And even the third point, when x is square root of 3, we do have an inflection point again. So now, at this moment, I can completely announce that this function has actually 3 inflection points at these 3 x values. I can call these like A, B, C. So negative square root of 3, 0, positive square root of 3, I can plug these values in the equation of the function actually, and I can calculate the y-coordinates of these inflection points. If you plug in 0, it's going to be 0. If you plug in negative square root of 3, you will end up with minus root 3 over 4. And when you plug in positive root 3, you get positive root 3 over 4. And these are the inflection points of this rational function. Inflection points. This function has 3 inflection points, and these are the coordinates of those inflection points. Next thing I have to state is the intervals of concave up, concave down, which there's no room here, so perhaps I'm going to erase this part so that I can write the answer at the top. So concave up and concave down, the intervals. So let's look at the chart. The graph is clearly concave up from negative root 3 up to 0. So negative root 3 up to 0. We take the union of that interval with the other interval from square root of 3 to positive infinity. So this is called the interval of concave up. Interval of concave down for the other one would be from negative infinity. You see that y double prime is negative, up to negative root 3. And then we have from 0 to positive root 3. And that's it. So if you combine these two intervals where y double prime is negative, you will be finding the interval of concave down for this function. And if you take parts of the chart where the second derivative has a positive sign, that will be the interval of concave up. So we answered the question. We found the intervals of concave up, concave down for this function. We know exactly where the graph is concave up, where it's concave down, and we also know the inflection points of this function. In the next lectures, we're going to learn more about this, and we're going to practice more. Thank you very much, and don't forget, where there is a will, there is a